Welcome to Nanoscribe's webinar with the title Scaling Photonic Computing. Today, we will be talking about the current state of photonic computing, emerging scaling concepts, and a variety of optical interconnect and packaging approaches enabling low-loss, high-performance photonic coupling. We will not only show results today, but also witness a live demonstration showcasing how Nanoscribe's technology aligned two-photon lithography enables the precise fabrication of scalable coupling structures. My name is Jan Stabados. I'm a product manager at Nanoscribe. I'm in charge of our Quantum X systems, and I have the honor to guide you through today's webinar. And now, let's move to the speakers of today's webinar. It's my pleasure and honor to welcome a highly regarded expert in integrated photonics, Professor Wolfram Pernice. Professor Pernice is the director of the Kirchhoff Institute for Physics at Heidelberg University in Germany, and a recipient of Germany's most prestigious scientific award, the Gottfried Wilhelm Leibniz Prize of the DFG, for his pioneering research, which focuses on neuromorphic and quantum photonics, nonlinear integrated optics, and scalable photonic computing architectures. He has authored numerous high-impact publications in these fields, and currently also leads the EU Horizon 2020 research project Phoenix. Outside of academia, he has also launched several spin-off companies. Two of them are in Germany, Pixel Photonics and Link Photonics, and there's also Salience Labs in the UK. In today's webinar, Professor Pernice will outline the technological potential of photonic computing. He will discuss scaling perspective beyond electronic architectures and emerging neuromorphic hardware concepts, introduce the integration challenges that currently still hinder deployment, and explain the packaging requirements for scalable, application-ready photonic systems. We also welcome Erik Jung as our second speaker of the day, who is a senior PhD researcher in Professor Pernice's Neuromorphic Quantum Photonics group at the University of Heidelberg. His work focuses on scalable photonics packaging and advanced fiber-to-chip interconnect technologies. During his PhD, he developed a low-loss plug-and-play connector enabling robust and automated PIC assembly, and contributed to high-performance packaging strategies for next-generation photonic systems. Today, Erik will present a scalable photonic packaging concept for wafer-scale packaging designed for industrial implementation, compare established approaches such as edge and gradient coupling with advanced interfacing concepts, and as a key innovation, he will introduce the aforementioned plug-and-play fiber-to-chip connector he developed during his PhD, which highlights the advantages of passive alignment for volume production. And last but not least, I would like to warmly welcome my colleague, Nanoscribe Senior Process Engineer, Tobias Hose. Tobias is an expert in photonics and aligned high-precision 3D microfabrication. As part of his work at Nanoscribe, he has contributed to several national and international research projects, for example, the aforementioned Phoenix project. More specifically, his work focuses on photonic packaging application using Nanoscribe's aligned two-photon lithography and two-photon grayscale lithography technologies. He uses these technologies to fabricate advanced optical interconnects and scalable coupling solutions for integrated photonic systems. Tobias will demonstrate how aligned 3D printing enables highly efficient optical interfaces directly printed in place. He will explain the alignment workflow, the positioning accuracy, and show the advantages of aligned two-photon lithography. And he will also guide us through a live printing demonstration, showing how to get from an optical design to a printed optical coupler in minutes. And with this, it's my pleasure to finally hand over the airwaves to the speaker you've been waiting for. It's the first speaker of our webinar, Professor Wolfram Pernice, who will be introducing us to the topic of photonic computing. So Professor Pernice, take it away.
Yeah, I shall. Thank you very much for the intro. And I hope you can all see my screen. If not, shout. So, perfect. Then thank you very much for the kind intro and also for the opportunity to speak here about the research we are doing. It's really a pleasure to present this here in this webinar, especially since we are also very happy users of a Nanoscribe system. We use it basically every day in the lab for printing structures. And Eric will show you some of the nice features we can build with them. And that tool has also been somewhat instrumental for driving computing forward that we now use in the context of AI. It's also great that Tobias is here, with whom we have collaborated for many years now in the EU project, and actually also worked on improving the tools for printing such coupling structures in a hybrid project. So everything comes together very nicely today, and I'll sort of set the stage and explain a little bit why I think this is a useful technology for the field. So we come from integrated optics and build chips, and a few of them you can see here on my first slide. These are semiconducting chips, many made from nitride or silicon actually, and we use those for doing computations, low precision computations that have applications in AI. So we were very happy that AI actually took off in the last decade so much, since that is always a very good motivation for the research we do. And I'll try to put this a little bit into perspective. So we're talking about scaling today, and scaling hardware in particular. And I think this is a very nice opportunity, because it is also one of the driving themes in the AI world, especially now that AI models have become so powerful that hardware underlying the computational systems is actually almost getting to become a bottleneck. So this is a recent article that I pulled from the web, from the World Economic Forum, and it basically lays out the trajectory for AI hardware over the coming 5 years. And it's also saying that nowadays hardware is really one of the driving forces there, and also leads to the most valued companies working in this area. NVIDIA, you all know, 20, 30 years ago, not so many did know about NVIDIA. That was mostly for gaming, but nowadays GPUs are basically the core driving system in making large language models and such possible to be solved. So this is a very big market, and the investment in hardware is also very big, about 7 trillion in the next 5 years, and almost 700 billion alone this year in AI infrastructure. And it turns out photonics is in the long run maybe a good add-on for building this hardware, in particular if we think about scaling. Right now, basically everything in AI hardware is done via electronics. This is done via specialized accelerator systems built to perform very fast matrix vector multiplications. And you can see here the development trajectory over the years, growing very quickly. We are sort of here on the right end of the scale, where transistors are beyond 100 billions. And actually, if you look at some of the new graphic cards that came out, or AI accelerators rather, they already have more than 300 billion transistors, which is a huge number also in comparison of what our brain has. This is still one of the most powerful computers on the brain, but if you just count the numbers of the computational units, we are on par basically. So this is also a reason why GPUs have won the hardware lottery and have been scaled massively. But it's also a reason why people are thinking about new architectures to come. This basically has to do with some of the shortcomings of electronic systems, namely that they are all built on transistors. And as you all know, transistor scaling is also nearing its end. Basically, the fab lines are now down to few atoms systems. This is TSMC's 1.6 nanometer process. In silicon, this is more or less 3 atoms. So you can imagine it's difficult to go much further. Therefore, the way to improve this is by parallelizing many of such compute cores. This, on the other hand, uses a lot of power, especially for large data centers. And there are also challenges with latency. So basically the time such a system takes for processing AI data, which is also a reason why energy is becoming an issue. And there are also some articles from the news, just 3 here from the last years, where basically some of the hyperscalers are looking into very large power plants, nuclear power plants actually, to drive these data centers. So this may be well doable in the US, but in Germany, as you may know, this is a challenge since we don't have nuclear power plants anymore. And therefore, it's also not so clear what to do about scaling AI data centers. And hence, you can either think about finding new sources of power, or you can also think about finding new ways of building hardware. And this is actually what we are doing, since there have also been very nice developments in parallel in silicon photonics, which is maturing very, very quickly and also scaling very nicely. And it turns out such a platform cannot just be used for communication. This is probably where its primary use has been, so building transceivers and receivers, also for wavelength division multiplexing. But I think one can take exactly the same elements a step further and go beyond digital communication by working with similar elements and driving them in an analog framework. And this way you basically end up in a way of building analog computers. So this is sort of the setting we have been working into, taking components that originate from the silicon photonics world. So basically modulators, lasers, photodetectors, maybe amplifiers for boosting signals, and then interpreting them in a new way as sources for signal encoding, and also developing the analog framework around it to build new computers that are very, very fast. The nice thing is this mapping works extremely well because linear optics are very good at transforming signals, also at high speed, and therefore you can replace some of the GPU optimized tasks directly on such a hardware platform. And in the context of AI, this is particularly promising because it takes over some of the tasks that are very power hungry on traditional hardware. So if you think about deep learning in a very simple picture, this would be some way of classifying images, for example. You can imagine that you propagate such a structure through a deep network and transition between artificial neurons in this very, very simplified picture. But the transition between layers in this case would be exactly linear mathematical operations, the aforementioned matrix vector multiplications that GPUs have been optimized for. And it turns out this is a good way of looking into accelerating because the major part of effort in such systems actually goes to performing such matrix multiplications. This is a slide that I stole from a presentation from IBM a few years ago, where actually the comparison of effort is shown for different tasks in AI, such as speech processing, language processing, or vision processing. And the matrix multiplication part is the red bar here. And you can see in all of the 3 cases, well over 70% of this effort actually goes to this particular mathematical operation. And the nice thing is this operation also maps very nicely to photonics, because photonics is good at doing 2 types of basic signal manipulations, namely multiplying signals and also adding them together. And therefore, we're sort of in a fruitful area where you can basically tie this all together and come up with systems that perform these operations at very, very high speed. Let me briefly explain to you how this works. In principle, if you want to multiply 2 numbers, you basically need a few ingredients. You need to be able to encode these signals in different properties of light as our signal carrier, and you need some way of determining the result of this operation. So say we want to multiply numbers A and T together and know the result P, and what we would do in a photonic framework is encode the first number in the amplitude of a light field, for example, the second one in the transmission factor or an attenuation, And then our result would be the measurement of the light that is coming out at the other end. And of course, you can do this nicely. You obtain a laser diode. With this, you can set the amplitude by programming it. You then would have to program the transmission factor. This you could do with a silicon photonics chip. And if you want to know the result of the multiplication, you have to measure the power at the output. This is attractive for us because the components are already available from silicon photonics, as I mentioned. But also they work at typical telecom frequencies, so at very, very high speeds compared to digital electronics. And therefore you get your answer in extremely low time frames. So this is where latency matters. And you also, in principle, can do this relatively efficiently as long as your components are efficient. If you want to scale this, all you have to do is basically make many of such devices. So one approach we used, for example, is take a light source that provides not a single input laser, but so to speak, many of them. This is a frequency comb, for example. We would encode our image in the input vector. So basically, we would use several modulators for setting the amplitudes of each individual wavelength. Then we would add them together in a photonic circuit that basically couples all these different wavelengths from separate input waveguides into a common output waveguide, where we then can perform the result by measuring the total power with a photodetector. And by doing this, what we perform is a very basic vector-vector multiplication. We multiply the input vectors times the modulation system. So therefore, multiply the numbers a and t, and we get the full result of this operation in a single shot. And then, of course, if you can do this for one row, you can do this for many. And there you go and have a mathematical matrix implemented on a chip. Now, this has been quite successful, and there are many groups working in this area. This is an example from a group at Tsinghua University, which has shown that such an optical operation also is very, very effective. So you get your answer not only at high speed, but you also get it at very low output power. So the metric here is the number of operations that you can perform with a watt of power. And in this system, for example, what the group showed is that you can do diffractive image processing at an efficiency of 160 tera operations per watt, which is quite a good number. Also, if you compare that against efficient supercomputers, on the right-hand side, you can see one of Germany's new supercomputer, Jupiter, which is in Jülich. So this one delivers about 60 tera operations per watt, significantly lower, but of course, it is a more general purpose computer. Now I'll spend a few minutes explaining how we build those chips. We do this in the clean room. We don't work on wafer scale, but on a chip level. So we write our structures by electron beam lithography, and with the nanoscribe, as I will show you in a little bit, we etch those into our favorite semiconductor, silicon nitride or others. Then we get these nice looking chips here. If you zoom in a little further, then you can also see the tinier structures which are needed because we work on the sub-wavelength scale. These are different types of resonators in silicon nitride and silicon, also photonic crystal structures as such. So these are the typical elements we use for implementing these transmission factors for matrix vector multiplication. A challenge that we have had for a long time is how to get light into these structures. You can see here that these are small, but also if we compare them to an optical fiber, the scale is even larger. So we like to talk to these chips via fibers because then we can use these telecom equipment that we already have. But the waveguides that we fabricate, which you see here at the bottom, are way smaller than a fiber core. This is, of course, a common knowledge problem. It's actually also to scale, but you see if we stick this directly onto our chips, we will not be very efficient. And this is where a nanoscribe comes in. This enables us to actually talk to these chips. So we use two-photon polymerization to basically write fancy 3D structures directly onto these little waveguides and therefore transform a very small and confined waveguide mode into something that resembles much more an optical fiber. And this has really, as I said, already been an enabling technology for us. It's also something that is heavily driven in Karlsruhe and Heidelberg through a excellence cluster 3D matter made to order, where these structures are built. On the chip, you can see a selection of such coupling structures, and Erik will give you much more details of how they work. They basically are total internal reflection systems that transform an in-plane mode into an out-of-plane focused beam, and this beam we then can collect with an optical fiber to read out the performance of our system. What then needs to be done is house this all in a framework that is compatible with a computing architecture. This is the latest system that we have built. It's a box that has all the driving electronics for the lasers, modulators, amplifiers, and detectors. You can also see here in this circuit board on the right-hand side the chip that is actually doing the optical calculation. It is fiber coupled through a special interface, and the rest is actually electronics, but it's small enough that you can fit it in a car or use it as a desktop, and it does exactly this acceleration. And I think at this point, I'm way over time, and I'll hand over to Erik. I also thank him and the rest of my group for doing this. This is basically the team that builds these optical computers and realizes all the systems in the clean room.
So thank you very much for this great introduction to the field of photonic computing, Professor Pernice, and thank you also for explaining why we should care about photonic computing as daily AI users, as I'm sure most of the listeners here are. I can already see some questions, which we will answer in dedicated Q&A session, but so keep them coming in the meantime. It's in the Zoom toolbar. You have a Q&A button there. You can ask your questions, and we will make sure to answer all of them. But first, as Professor Pernice already introduced, it's my pleasure to hand over to Erik Jung, who is a senior PhD researcher in Professor Pernice's group. So, Erik, take it away.
Hi, and thank you for the kind introduction, Jan, and also Wolfram. Can you see my slides?
Yes, we can see
Perfect.
them perfectly.
I want to start by presenting state-of-the-art packaging concepts and their respective challenges and opportunities, and then, as Jan already mentioned, introduce a novel plug-and-play packaging concept. This project was realized in the framework of the Cluster of Excellence 3D Matter Made to Order at Heidelberg University. Let me briefly check my laser pointer on. So this is all, you can also see my laser pointer.
Yes.
Perfect. As Wolfram already mentioned, photonic integrated circuits, which you see here, but be aware only this small part is a photonic integrated circuit, have a lot of powerful applications. For Wolfram has shown you on-chip photonic matrix vector multiplication schemes, which are used in photonic computing. For example, here to detect the edges of the zebra via a photonic processor. They profit of the low latency time, the low energy consumption, and the high degree of parallelization of photonics. Especially the high degree of parallelization is a great advantage in photonics and especially important for this talk. So I want to briefly explain it one more time. So we have here in the photonics, we have the great advantage that we can do wavelength division multiplexing, where different information is encoded in different wavelength bins. You can see here a visible spectrum. So spanning from 300 nanometers to 600 nanometers, and different wavelength bins symbolized by those squares. And those wavelength bins we can all on the same time we can use optical waveguide to transport all those wavelength bins at the same time in one optical waveguide. So that's why we have a high degree of parallelization and a high data rate. As we have now understood this, let's circle back to this image on the left-hand side. So we can see the photonic integrated circuit is interfaced with a fiber array, so a block of fibers from the top here, and is also in the and with that we are getting the data onto our chip. It is also interfaced with electronic signals via those PCB, and this setup looks already quite packed, especially if we are considering that this fiber array needs to be perfectly aligned relative to this chip. So normally this fiber array or the chip is placed on a 6-axis stage, so 3 rotational degrees of freedom, 3 translational degrees of freedoms. And we need to optimize this position till we have the optimal transmission of the coupler. Especially if we want to fix the fiber array in place on top of the chip, we need to monitor. We normally glue it and need to monitor the transmission over multiple, over a large time scale due to the shrinkage of the glue. As we now talked a lot about how we need to align fiber array and chips, let's continue with different packaging concepts. There are basically two packaging concepts around, which are in-plane coupling, where the chip is addressed via fiber array in the plane of the photonic integrated circuits. Here, this is a chip which is used for in-plane coupling, and I'm highlighted the in-plane couplers here. They normally have the advantage they are quite broadband and low loss, but as you can see, all the couplers need to be routed to the edges of the chip as well as the electronics. So we have a reduced degree of design freedom for our chips. That's why out-of-plane coupling is also an option to use to couple to our photonic chips. Here I highlighted once again on a chip with basically the same area, all the out-of-plane couplers, and you can see that you have a factor 10 to 20 more addressable devices on the chip. So this gives a high degree in design freedom. And another advantage of those out of plane couplers is that they normally can be written within the photonics layers, because they are normally those type of couplers, those grading couplers. However, those grading couplers do have a great wavelength dependency. So what you can see here is the transmission spectrum, so wavelength against transmission per coupler. I want to illustrate what this means once again using this visible spectrum, which I showed you beforehand. So here we are working in the telecom, as Wolfram already mentioned, but as an example, I show you the visible spectrum because I can't. There are no visible wavelengths with which I can encode that. So here's the visible spectrum, and if I would use a grading coupler to couple this visible spectrum inside of my photonic chip, the coupler would absorb a part of this transmission spectrum, and it would more look like this. So yeah, basically a couple of those wavelength bins are gone. This gets even worse if we are looking in real scale units onto that problem. So if we are looking at the peak transmission here of our grading coupler, I will now reduce the brightness of my slide accordingly. So basically the image of the slide is sent through the grading coupler at this wavelength, and this results in this transmission. And if we go 30 nanometers away from the optimum, so in the visible, the equivalent from going to green to yellow, you only see, so we are there, you only see that anymore. And this is only the efficiency which is absorbed by the coupling interfaces. So as you can see, there are a lot of open challenges in the domain of photonics. For that reason, Wolfram came at the beginning of my PhD to me and came with this wish list for photonic packaging. So we want to profit of the full multiplexing capabilities of photonics without loss of data. So we want low loss and broadband coupling. We want to interface multiple ports at the same time, so that we can realize in that manner some photonic applications and not only address individual ports. As I showed you on the right-hand side, we also have electronics on our photonic chip. So we want to also have the capability to co-package electronics and photonics. And last but not least, we want passively self-centered alignment like in electronics. So we sat together at University of Heidelberg and we came up with this coupling concept. So here on the left-hand side, you can see a sketch of the coupling concepts. You have so we are basically using a fiber array, an MTP cable, which is a fiber array, but with included alignment pinholes, and fabricate the alignment counterpart directly on the surface of the photonic chip, as you can see here. So those pins are the alignment counterpart onto which the MTP cable is at the end plugged. Coupling is done via those total internal reflection couplers, which will be discussed in detail in the upcoming slide. This is a multi-step procedure where the nanoscribe technology is helping us in an insane manner. So in the first step, with the small feature set of nanoscribe, we write structures with nanometer precision and optically smooth surfaces. In the second DLV step, also with the technique of nanoscribe, but this time with the 10 times objective, we are writing disalignment pins as well as some spacers so that our fiber array is not crashing into our photonic integrated circuit. Here, this preset is optimized for speed and micrometer precision. And you think, so this will take ages, but also those pins are fabricated within 20 minutes using, and they are 2 millimeters high, and they are fabricated within 10 to 20 minutes with the technique of nanoscribe. In the third step, we deploy digital light processing printing to print a pre-alignment structure, which you can see here, which buries basically the weight of this MTP cable, as this is a centimeter high glass fiber block. So as I said, let's come back to the coupling interfaces. I was lucky to have a very competent predecessor, Helge Gehring, who developed the first total internal reflection coupler. Here on the left-hand side, you can see such a total internal reflection coupler on a silicon nitride substrate. So you have here the silicon nitride substrate and such a polymer coupler on the substrate. The polymer couplers are written with aligned two-photon polymerization on top of the silicon nitride substrate. They are based on total reflection and not on diffraction in comparison with the grating couplers, and are therefore very broadband. They consist normally of 4 distinct sections: the mode transfer section, where I transfer the on-chip mode to the polymer mode; the mode field widening section, as Wolfram mentioned, the mode field diameter of the fiber is a factor 10 to 20 wider than the one on-chip; and then a total reflection plane, which redirects our light beam out of the plane of the chip to our fiber array, and then we have a focusing lens atop. This focusing lens focuses down the light beam and mimics the behavior of the diverging beam out of the fiber, and this is also the component which we optimized in comparison with Helge's original total internal reflection couplers. Here on the left-hand side, you can see a part of a chip which we fabricated with this technology. So we have printed 115 times 115 different coupler geometries, each 6 times. So in total, 900 geometries done. And with the technique of nanoscribe, this is possible within one night slot. So one coupler is taking approximately 1 minute with aligned two-photon grayscale lithography. And if you cycle back, or if you are still a GT user, we also fabricated this beforehand with the GT, and it took 16 minutes per coupler. So there's an immense increase in speed using grayscale lithography. On the right-hand side, we can see the transmission spectrum of the 3 nominally identical best couplers, showing the low standard deviation of the coupler transmission spectrum and basically their wavelength independency, plus their peak average transmission at 1550 of 0.45 dB. If we apply the same transparency filter, so basically sending this image through a total internal through a total internal reflection coupler, this results in blending down my screen in that manner. So basically no deviation in between what you saw beforehand and what you see right now. To demonstrate the packaging concept is working with multiple ports. We interfaced a photonic matrix with 16 ports. So here you can see an image of this photonic matrix, here the pins, and the 16 ports of the photonic matrix, and compared the transmission of the individual ports to the one of a grading coupler. If we play the same game as beforehand, but this time on the left-hand side, we are using the grading coupler to couple in, and on the right-hand side of the picture, we are using the 3D coupler to couple in at the peak power of the grading coupler. This results in that image, and if we are going further away, this results in that image. So basically, we have for the already packaged matrix vector, already packaged plug-and-play connector, a higher transmission in comparison with the state-of-the-art grading coupler, and this is only possible with structures based on which are not based on diffraction. If we are now look at the close-up of the transmission spectra of the individual ports, we can see that they also have the same behavior in general. So all the 16 transmission spectra, they show basically the same peak performance and also the same behavior, the same wavelength independent behavior of the over the different matrix ports. With that, I am coming to an end and summarize that we as a team basically fulfilled the wish list which Wolfram gave me at the beginning of my PhD. So we have broadband and low-loss optical coupling, reproducible multi-port signal transmission, photonic electronic co-packaging, and passively self-centered alignment. With that, I want to thank if you want to read more details about our plug-and-play setup, for example, the coupler optimization, the alignment tolerances, or the reproducibility over multiple attachment cycles, please scan the QR code and read the full publication. I want to thank the group of Wolfram Pernice, my collaborators, Nanoscribe for their great technology, and the funding agency for their support.
So thank you very much, Eric, for these amazing results and for introducing the plug-and-play connector, which was, by the way, also featured on the University of Heidelberg's website and on Nanoscribe's website some time ago. So yeah, go ahead and read the publication. We will now get to the first questions and answers session, and I can already tell you that we have way too many questions to answer all of them here. And since we are a bit over time, we will only answer a few, but my colleagues are answering other questions in the background. And if you don't get to your question, first of all, there's a second Q&A session coming up, so keep the questions coming. And if you also don't answer them there, we will answer them later in writing, so all questions will be answered. But maybe I would like to start with a question for Wolfram Pernice, and this question is about the current main bottlenecks for photonic computing. So basically, you've outlined really nicely how we need photonic computing because, yeah, we need this efficiency, and they have, of course, lower energy consumption. But the question here was, what's currently preventing us from already deploying these in the field? There were some people here who guessed it's maybe that you have to first convert electronic signals to light signals, or is it maybe the losses between the photonic components or something else? So what, in your view, is the main bottleneck that's currently preventing deployment in the field?
Well, going from a prototype to a commercial system is a long way, and that needs commercial effort, which is underway. But I think it takes time, and a key challenge is, of course, that these are high-speed signals. So you need high-speed and also efficient analog electronics to drive a multi-input output system. So this is demanding in terms of ASIC design, and also a challenge for scaling. I think this is maybe the key bottleneck that has to be done, and probably also making sure that this is compatible in terms of accuracy with the demands that current AI systems have.
All right, thank you very much. There are, so maybe because we're a bit over time, I would keep this short now and just ask Erik two questions that came up. They're rather short. One was about the coupler that you showed, the total internal reflection coupler. The question was, how did you come up with this design? Because of course, printing is one thing if you have the design ready, but how was this design done? So what was the tool that you used to come up with these designs?
So we basically used FTDT simulations, so finite elements, finite elements, and deployed COMSOL multiphysics, and they are used to calculate a lot of overlap integrals to determine the efficiency. But in case you are interested in that, this is in details in our publication.
All right, thank you. And there was another short question on this, so about the total internal reflection coupler. The question is, so since you seem to have an adiabatic coupling between the total internal reflection coupler and the silicon nitride waveguide, the question was, what's the distance there, or do you etch a channel in the silicon dioxide to guide the placement of the coupler, or how do you make sure the coupler is in the right position?
So we are making sure that the coupler is in the right position with the alignment tool of Nanoscribe, if this is the question. But we don't etch away any silicon. We only etch our silicon nitride waveguides, and as the substrate has a lower refractive index, then so the silicon dioxide underneath has a lower refractive index. The mode couples to the polymer waveguide instead of the underlying silicon dioxide.
Mm-hmm. All right, thank you very much. We have a lot more questions, and as I said, we will have a second Q&A session, and I think there we can give ourselves maybe a bit more time to ask these questions. But before doing this, it's my pleasure to hand over the microphone to our senior process engineer, Tobias Hose, who is going to show us how to get from an optical design to a printed optical interconnect using Nanoscribe's technology. So basically something that also Erik showed. And when I say show, I really mean it, because we'll also see a live print demonstration using a Nanoscribe Quantum X-Align system. So Tobias, take it away.
Okay, thank you, Jan, for the kind of introduction. You can see now my screen, right? Okay, so let me give you a quick look inside our lab here in our headquarters in Karlsruhe. This looks the lab where I'm working in, and we have here a small print farm with our Quantum X Align systems. And basically here is the place where we push the limits of two-photon lithography, where we develop industrial processes for our customers, and where we run also feasibility studies for prospects who are interested in our two-photon technology. What can you do with our technology? You can do prototyping, you can fabricate templates for mastering, and you can also do direct manufacturing of optical elements, as you have seen already before, these out of plane coupler. You can print lenses on the edge of chips, or you can also use it to produce lensed fiber arrays. We offer different print sets for this. So for example, there's a small feature set is used for highest precision, as Wolfram do it in his group. With this set, you can print also these filigrane tapers. Then we have the medium feature set, which is a very high versatile print set with which you can print arrays of these lenses on a chip edge, but still you get high optical quality lenses. Then we also have the large feature set with which you can print millimeter-sized optics, for example, for multimode applications. And the large feature set has a nice feature that it has a very long working distance, and with that you can also do backside detection. But to print cool or good working optical elements, you not only need the hardware, you also need a software that can take care of that, and that is also very user-friendly. And here you see a screenshot of our NanoPrint X software, and what we did, especially in the project Phoenix, with the joint project with Penny's group. As you have seen, they needed to print a lot of sweeps of their structures, and something like that you can very easily realize with our software. Inside the software, you can define your interconnect you want to print. You can also load the GTS file or your wafer map, parts of that, align the structure inside the software to the fiducials which are on your substrate. Select the process parameters, send it to the printer, and like that you can easily get fabricated hundreds of these out of plane couplers. As Wolfram mentioned that in his presentation, they basically do that on chip level, but our tools not only work on chip level, you can also print on wafer scale. What you see here is an 8-inch calibration glass wafer. And on each of these chiplets here, there are marker structures. And to each of these chiplets, we printed micro lenses. So the whole wafer is populated with lenses which are aligned to these marker structures on this 8-inch wafer. You cannot print only optics. This is a structure my colleague Mareike showed in the last webinar. You can also print mechanics. What you see here is basically a clamp structure in which we put a fiber. So this fiber here, this is an optical fiber, which is clamped into this clip. And since this clip is printed with our align tools, the clip is, or this mechanical structure is perfectly aligned to marker structures here on the chip. So this is a photonic chip, and under this optical element here we have a lens and also again a total internal reflection mirror. Underneath here there is a grating coupler and then the waveguide, and like this you can easily align your fiber, clip it into this clip, and couple light from the fiber into the grating coupler on your chip. And this also works on wafer scale. What you see here is a 6-inch silicon nitride wafer from IMS Chips in Stuttgart. These bright spots here are basically all these fiber clamps I showed you in the SEM image beforehand. And this bit less brighter structures are the waveguides, which are connected to the grating couplers. And all this is printed with our system QuantumX Align. The QuantumX Align comes with our Two-Photon Grayscale Lithography, with which you can reach high optical quality surfaces with a low roughness and a very good shape accuracy. Inside our system, we also have a confocal module with which we can align the structures you want to print to predefined structures on your substrate. And like this, you can achieve low loss optical couplers, and they are printed precisely at the position where you need them. Here's a very simplified sketch of our lithography system. We are using a femtosecond laser, which is focused through an objective into the photoresin, and it excites the photoresin to polymerize. And by using fast scanning galvo mirrors, we can steer the laser back and forth through the resin. And on the same time, we are moving with the stage, which carries your sample along the axis of the beam. And like this, we can create 3D microstructures. And we included here a confocal microscope inside the system for detecting alignment markers or chip edges of your substrate. And since the same laser and the same optical path are used for printing and for detecting, we are already inherently calibrated. And like this, you can achieve very good alignment accuracies down to 100 nanometers. This I just want to show briefly, since Wolfram has covered this. If you want to couple from one substrate to the other, for example, from a fiber to a photonic chip, you need to match the mode fields to each other because they are typically vastly different in sizes. And also the alignment accuracy or the alignment tolerances are directly connected to the size of the mode field diameter. So how you can overcome these challenges, you can put optical elements onto the substrates, like collimating lenses, for example, and then you increase the 1 dB alignment tolerance drastically. So if you have on this right-hand side here in this graph, it's shown the alignment tolerances for example, a 3 micrometer mode field diameter compared to the one here in blue with a 25 micrometer mode field diameter. But this means on the other side, you move the alignment challenge from the packaging step to the two-photon lithography step. But as mentioned, with our system, we really reach these high alignment accuracies. And like this, we can precisely print the structures to the output of the substrates you want to couple with each other. But I want to go further and not show you only this theoretical sketch. I really want to show you how that looks in the real world and how do we come from the sketch to an image like this. On the left-hand side, we have a fiber array unit, and we printed collimated lenses onto each of the fibers. And on the right-hand side, we have a silicon nitride chip with these loopback waveguides, and we printed also collimating lenses onto the chip here. And like this, we achieved a low loss coupling between those two substrates. And I want to guide you now shortly through our NanoPrintX software, how to create there these freeform microlenses, how to precisely align them to the marker structures of your chip, and how to use the dose compensation over the chip edge. For that, I'm using the medium feature set, so using IPS as our standard resin, the 25 times objective, and the QX system QuantumX Align, which is down in our lab. So now let me shortly switch to the screen to our software. So here you see basically the main view in the middle. It looks like a CAD tool. You have here the lens, which we want to print. The lens has been simulated before. Now here we are. Sorry. The lens has been simulated beforehand. In Nanoprint X, we are using a conic lens description, a conic lens formula, and the parameters of that you can directly type in here, like the curvature of the lens or the conic constant. And like this, the lens is directly created in Nanoprint X. You don't need to create an STL file externally and load it in. You can do that directly in here. We then have here some adhesion structures and support structures around the lens. And to each of them, I assign the 2GL IPS preset. In the presets option here, you find all our standard preset that we developed here at Nanoscribe. I use that basically for all of the structures. Just around the chip edge here, I use a adapted preset with a little bit of less laser power to avoid bubbling around the interface between the silicon oxide of the chip and the back silicon. Then we have here the so-called dose compensation. So when printing from the top over the chip edge, our laser spot is a little bit clipped. For that, we compensate the laser power. So this is done here with this node. And I forgot to mention, so here on the left side, you basically see the tree view. And on the right side, you have always the properties of the node we are looking in. We then have the marker aligners. The markers, we typically use these double square markers. They are then confocally detected inside the machine, and the structure, which is defined later on underneath this node, is then aligned to the detected position of the marker. For detecting the interface and the tilt of the chip, we are using an interface aligner. Then we also have an edge aligner to precisely detect the chip edge and the rotation of the chip. And last but not least, we have the so-called coarse aligner. And with this coarse aligners, we interact with the machine. I will show that later on or in a minute. And we can tell the machine where is the chip, your substrate, located in the machine coordinate system. So the machine knows where is the chip, and then start the printing printing job. Then we choose the medium feature preset, print set for this demonstration, IPS as our standard resin, and as a substrate, I choose here silicon. We then load it to our machine. It says upload successful, and then we move over to NanoConnect X. NanoConnect X is a software to remotely connect with our printer. It's the same view here, what you have as you standing in front of the printer and using the touch screen. We then start the job we just uploaded here. Then it's doing some pre-processing, loading the structure into the RAM of the PC. And while with double-clicking inside the screen here, I can move around on the sample. Now it's asking me about the coarse aligners. So where are they? I choose them to be here, those markers on the chip. So this is the front marker. I confirm the position. I move to the back marker, confirm it too. Now the machine has already got 2 positions. It has already an idea where is the chip and how is this rotated. To the 3rd position, I automatically move. I see this is already more or less correct. Confirm the position, and now the whole job is running automatically. You see the chip is now getting a little bit defocused, so the machine is doing the interface finding, doing a Z-scan, finding the interface, then doing an edge detection, doing the marker detection, and when it's done with that, it's moving down along the facet of the chip and basically starts now to print. Here, very down at the edge of the chip, you can see now the laser moving back and forth. I think due to the latency of the zoom, you cannot see it moving as quickly as I see it live now. But you see, or what you see is not exactly the laser beam; it's the fluorescence of the resin. And now you see here the support structure already forming. When it's polymerized, it's changing a little bit the refractive index compared to the liquid state. That's why we can see it. Now you see here the lens forming, and you also see here right at the chip, it's printing with a little bit different laser power. You can see that here also in the raw view. So we have 2 camera views. The enhanced contrast view is sometimes helpful to see different things on the cameras. And we almost more or less done. You see here now printing on top of the surface of the chip. And after your print is done, here we are. It says we are done. Took us now printing 1.5 minutes. After your print is done, we take it out of the printer. We develop the sample, washing away the unpolymerized resin. And then one thing you can do is taking it to the SEM and getting nice images like this. Here we have the array of those lenses printed to the chip edge, very well attached, and the lens surface is nicely smooth since we are using the grayscale lithography. Then, as mentioned, we also use it in a real coupling experiment, coupling from one fiber into the chip, propagating through the loopback waveguides, getting out here again and coupling back into the fiber. Like this, we had about 40 interconnects in total and an average coupling loss of 1.5 dB. We then went a bit further and did some environmental tests with these printed structures. Here on the bottom, you see those collimating lenses on the fiber area unit. And we took it put it into a climate chamber for 1,000 hours at 85 degrees Celsius and 85% humidity. And afterwards, after these 1,000 hours, the beam profile and also the transmission basically stayed unchanged. We also conducted some other environmental tests like laser induced damage thresholds. So at 520 nanometers, for example, we are with IPS at 45 kilowatts per square centimeters. And also we did some other temperature tests, for example, for reflow soldering, because that's what you need for co-packaged optics. And with this, I would like to give the word back to Jan.
So thank you very much. And thank you for the amazing live print demonstration, Tobias. We really appreciate the many questions we have received. But now we will get to our second questions and answers session. And yeah, as I've already said, some of you may have already received some answers in the background. Some of you will also not receive an answer in this session, but in that case, we will follow up later with you. And I would like to start with, in fact, the question about the image I'm showing. This is an image Tobias also showed, and it was a question about what the application was here. So why were these why were these fibers clipped this way? And what was printed here? How was this done?
So this was basically to also in a joint funded project where we aim for a quantum sensor, and for this we used a photonic chip from IMS Stuttgart, where we had grating couplers also on the chip, and we wanted to place the fiber stable in place. We needed only a few fibers. We didn't need a whole fiber array. And for that, we came up with these clips. So basically using a single fiber. And as I said, the grating coupler is basically underneath the optical structure. And then you don't need to have an active alignment. You can passively align the fiber. And also then during the coupling experiment, the fiber stays in place and is not drifting away.
All right, thank you very much. We've received multiple questions for Eric on the alignment pins. So you showed that you not only print the coupler itself using two-photon polymerization, but that you also print the pins. And people here asked whether this was tested in real life or how well it worked, because of course it's polymers, so people we're wondering if these are stable enough to be used and how you use them. Do you need lab level equipment to use this, or how does it work?
So I think we were also impressed at the beginnings how strong basically the dedicated resin IPXQ is, especially after you were curing it with UV. But this is also depending on the substrate. So there are substrates where the UV curing induces more stability, but also less stability. But there are also substrates where it induces less stability. So this is this is very substrate dependent. But I think this is an issue which landed in the backup slides, but we did attachment reattachment cycles and measure the transmission for the ports, and we also get there quite reproducible results which you can find in the appendix of our publication.
Thank you. So again, if you're interested in this, and I see multiple people are interested in this, go and read the publication. It's even open access if you need more details. There's one question for Professor Pernice. You mentioned silicon nitride as your substrate of choice. Now, looking around the photonics realm, it looks like there's many substrates out there: lithium niobate, lithium tantalate, aluminum nitride, and so on. So do you think that at the end of the day, this field will agree or merge towards one substrate, or will it stay this big zoo of substrates that we're seeing right now?
I think that's a good question, but probably the answer is that for different applications, you want to use different materials. So silicon nitride has the advantage that it's easy to come by, has very good properties, has the disadvantage that is mostly passive. So I think it depends very much on what you need to do. If you need active functionality, then you need to go to more complex materials. If you can live with passive structures, then I think cost is a key driver. So I would expect that you will always have a range of materials.
All right, thank you very much. Eric, there's another question regarding the different steps you showed. So first you print the couplers, then you print the pins, and then you use digital light processing to print even more parts. And there's someone here who asked, how you make sure that all of these are aligned to each other properly, and how do you make sure this is correct, at scale, because maybe doing it once, yeah, you maybe can get lucky, but you showed that you do this you do this hundreds of times. And so the question is, how do you make sure all of this is aligned?
So I think so for the first two steps, so for the nanoscribe involved steps, Toby has basically shown the solution, which is a quantum X align, and just making use of the confocal module beforehand. For the pins, it is even possible to do this without a confocal module, because we started to develop those pins when nanoprint X align was not yet available for the 10 times objective. So there also the accuracy of the stage is quite appropriate. And then we attach this pre-alignment structure. We attach by pins next by on which we stick this pre-alignment structure. But this is also depicted in the publication, and due to a lack of time, I didn't go in detail through how we attach the pre-alignment structure. But in principle, this can be found also in this publication.
All right, thank you. And since we're a bit over time here, I would just briefly ask two more questions. And then I think if your question hasn't been answered yet, you will have to wait for us to follow up, but we will be quick. One question goes to you, Toby. So you've shown how these polymers behave at higher temperatures, and there were multiple questions here asking whether such couplers or coupling structures could also be used at cryogenic temperatures.
This actually might be the right question for Wolfram, so I think
maybe then I should pass it on.
Photonics is using them. So as far as I know, they withstand those structures, these temperatures.
Yeah, we use them also at cryo temperature, and they are very stable.
Right. Thank you very much. Can you maybe say what temperatures we're talking about? Because some people asked here if what.
So below 2 Kelvin is fine.
All right. All right. Thank you very much. So then we have an answer to that. And there was another question, maybe Eric, this one's for you. You showed your coupling concept. And of course, I mean, one of the main points that all three of you made was that the mode field diameters, you have to make sure that those match. How do you select the mode field diameters? How do you design this? And what are typical achievable mode field diameters?
Sorry, I don't fully get the question. Can you somehow rephrase it?
Yes. So there was this slide where you showed that, of course, a fiber has a much bigger mode field, or is much bigger than a waveguide, and of course, light coming out of the two will not couple efficiently, and this is solved by printing optical structures with the nanoscribe system. How do you design the mode field diameter of those lenses?
So the mode field diameter of the lens coming out of the fibers is normally around 10 microns, and then you need to also take into account the natural divergence. This is for a focal distance of 15 microns. It is a factor of 1.5 approximately, and this can be compensated in 100 microns of approximately 100 microns of coupler length. But there we don't use an adiabatic widening of the mode field, but in adiabatic mode field widening strategy. So this saves us some space.
All right. Thank you for the detailed answer. And with this, since we're quite over time at this point, I would like to thank our three experts, Professor Wolfgang Pernies, Erik Junge, and Tobias Hose, for their fantastic contributions to this webinar. I would also like to thank you, our listeners, for your active participation. If you've asked for some form of follow-up, please rest assured that we will follow up with you. And if you've asked a question that we haven't answered yet, we will reach out to you by email. If this webinar got you interested in Nanoscribe and you'd like to get to know our technology better, please don't hesitate to reach out to our sales department to schedule a product demo or to check the feasibility of your project, or with any other questions you may have. We're always looking forward to hearing from you. If you'd like to contact any of our three experts, please also find their email addresses on the right-hand side of this slide. Thank you again, and have a great morning, afternoon, evening, or night, depending on where you're located. And see you in the next webinar, hopefully.